Hi, what I have here on the workbench today is an EC600-90 Electrophoresis power supply. It has an adjustable DC voltage output from roughly 10 volts all the way up to 4000 volts, and a maximum current of 300 milliamps. The maximum output power is rated at 300 watts, and you can limit the output by voltage, current, or power. Power supplies used for electrophoresis are usually found in biology or life science labs, and is mainly used for DNA fragment separations. My background has nothing to do with biology, but I watched a couple of videos on YouTube and found this process to be quite fascinating. Anyway, the reason I picked up this power supply at the first place is that most power supplies for electrophoresis operations are capable of outputting relatively high voltage and high current. And unlike high voltage bench power supplies, they are abundant in the second-hand market such as eBay and can be obtained relatively cheaply. So I wanted to see if these power supplies are suitable for lab use as well. And as usual, I do want to open this up and take a look inside, but before I do that, I wanted to first power it up and just take a quick look. Now, of course, first off the bat, electrophoresis power supplies are generally switching power supplies, which might not be ideal for a lot of applications in electronics, as the ripple noise could be significant. And we will take a look at the ripple noise as well after we do some initial testing here. Now let me power it up. And it powers right up. By the way, this power supply does come with a manual that you can find on the internet. And I downloaded this manual here. And you can see that it's actually fairly straightforward to use. By the way, the one we have here is this EC600-90, which is 4000 volts and 300 milliamps and 300 watts. And the same series has quite a few different models here. And here we have some very basic specifications laid out here. You can see that we have, for example, the regulation is less than 1%, and accuracy is 1.5%, and full scale of the display. And then we of course have the basic user manual tell you how to use this, but I went through this, so it's quite straightforward. Anyway, so now we can take a look at the actual unit, and we will play around. And so right now the output is off, and this is actually showing you the actual display. As soon as you start adjusting the knobs, it will show you what the set value is. So for instance, we can set the voltage here, and let's set it to 600 volts so that I can use my normal multimeter to measure it. Geez, I really don't like the beeping sound, and it's actually makes a beep every single time you touch something. And I'm sure there's a way we can probably make the beeping noise a little less later on, but nevertheless, that's how this unit is designed. So for example, we can set the milliamp range and to limit the, let's say, the current to 150 milliamp. And here's the wattage adjustment. By the way, so this one does have a pretty good velocity control. If you turn this knob faster, it will go by 10, and oh geez, the beeping noise is really driving me crazy here. But anyway, so if you turn it slowly, you can see it's going one by one. And as a electrophoresis power supply, of course it has a timer, because sometimes the drift of the DNA depends on the time, so you can preset the time that you want the power supply to be on. So anyway, so that aside, let's try power it on. What? Okay, so oh geez, okay. So it says it's no load. So apparently this has some load detection. Without connecting a load, I wouldn't be able to power it on, I guess. Let me try again. Nope. So okay, so I will be right back, and we will connect a load and go from there. So I just connected a 3 mega ohm resistor and it's working fine. Of course, a smaller resistance value would also work, but you're going to dissipate a lot of power when the voltage goes up. And anything larger than 3 mega ohm, it doesn't seem to work. So I will just leave it at 3 mega ohm. And the first thing you notice is that the residual value is at 10 volts. So that's quite typical because these kind of power supplies are usually meant for much higher voltage, at least several hundred volts. So it starts from 10 volts, that's perfectly acceptable. So now let's start powering it on and see what the output value reads. And it's taking quite some time. Okay, so now it started rising, and interestingly that this reading is somehow much slower than this one. Anyway, so we have arrived at 600 volts, so no problem. The reason I selected 600 volts is so that I can use this multimeter to measure without having to bring out the high voltage probe. So it seems that everything is working correctly. And of course we can fine adjust, so let's adjust this down. Let's adjust to 500 volts. And 501, 500. And no problem. But the first thing you see is that, you know, this first experiment we can already see that the reaction is really slow. So you wouldn't be able to use this power supply for anything that is a dynamic load and requires the power supply to adjust its output voltage rapidly. And so this one is mainly useful for something that is, for example, either a fixed resistance load or something that is very slow changing in terms of the load, and which for its intended purpose, the electrophoresis, and this is perfectly fine, but for a lot of the lab use, and you would want a power supply that can react much faster than this. So this is something that's the potential limitation of these kind of electrophoresis power supplies. And now, of course, we have been on for a while. You notice that the timer here started decreasing, and when it hits 0, this power gonna turn off. So that's another feature. Of course, you can just always adjust the time here. And by the way, all these knobs are velocity controlled. As you can see that I kept pressing it, it just started to increment faster and faster. So no problem at all. And so the next thing I wanted to take a look, and I'm going to turn the voltage down. So what I want to take a look is the ripple current, and because that also gonna have significant impact on the type of work you can do with this kind of power supply. So let me turn it to something reasonable so I can use a oscilloscope to measure. Let's turn it to 100 volts, and these things we don't need to worry about that. Okay, so let me bring out my oscilloscope and we will go from there. Okay, so now I have just brought out this scope, and let's try to measure its ripple. I set the channel 1 to let's see, oops, that's not channel 1, channel 1 to AC coupling, so we can see hopefully the ripple generated by this power supply. So now let me power it on. What's going on here? Oh, you see that the ground leak detection is on. Oh, I know what's happening. So let me unplug this. Hang on, let me unfortunately the only way I can do that, I think, is to power it off. So what I did not tell you is that this power supply, the EC600-90, also has a feature of a ground leak detection. So if there's any current that leaks into the earth, obviously that's when the ground fault occurs, and this power supply would cut off. So what I'm suspecting is that the negative terminal here is actually not grounded. So it's isolated. So what happens when you connect the oscilloscope's earth terminal to that negative, it causes this ground leak condition to happen. So the first thing some of you might suggest is, well, how about just use a isolation transformer? Well, in this case, it won't work because the isolation transformer, as I have shown before, it also has a earth terminal. So that earth terminal is actually common to the earth of your power supply. So even though the live and the neutral, those lines are isolated. So the only way I can think of doing that is to have a two-terminal plug instead of the standard three-prong plug. And I happen to have one here, so as you can see that this plug, and it has a standard three-prong layout, but it does not have the center pin here. So this one would be good for this type of measurement here. So let me swap out the plug and we'll try to measure again. Okay, so now let me enable this output again. And by the way, let me check if it's set to 100. Yep, it's 100 volts. That's what we want. So we turn it on. Oh no, so now it says no load. So I suspect that that ground leak, because see right now we still have this ground connected, so I suspect that that ground for some reason must be diverting some of the current so that the load detection no longer works correctly because some of the current is bypassed to the ground. So I guess I have to first power it up and then try to measure. So let's do this. So again, when you connect the earth pin of this oscilloscope into the negative terminal, there's some current going to be flowing through, and that probably messes up the measurement of that leakage. Sorry, not the leakage, the load measurement a little bit. So to compensate for that, I think what I'm going to do is I'm going to let the power supply output voltage to rise first, because after that is rising a little bit, the current flowing through the sensory resistor inside would be significant, so that hopefully the extra little bit of current, whatever, flowing through this leads will not matter. So let's give that a try. So now we're just waiting for the output to rise to 100 volts. As you can see, it does take some time to reach that 100 volts. So yep, so now we're connecting the earth terminal together, and you can see that there's no beeping, and the ground leak light is not on either, so which is a good sign. So let's now hook that to the oscilloscope. Whoa, so that is quite some ripple there. And let me first increase this to 500 millivolts and increase the time base a little bit, and you can see that we have some looks like a mains noise superimposed on it. So I'm not sure what is the correct level of measurement here. And I suspect that the mains noise could have something to do with this whole setup. So now let's not worry about that. Let's just look at the switching noise here. And the switching noise, as you can see, that we're looking at roughly about 500 millivolts, which is not insignificant. So depends on your application. For some applications, that this might be a deal breaker, but for most of the applications, it should be just fine. And so let's take a look at how that reacts to my output voltage change. And I need to be very careful not to make sure that it doesn't exceed 150 volts. Actually, I just want to, and as you can see, that really the noise actually does not change much with the voltage setting, which means that probably the 500 millivolts is a reasonable measurement of our switching noise. So that was the ripple measurement, and as you can see, it was a little bit on the high side, and depends on what you do, it may not be sufficient for your specific application, but nevertheless, it's okay for a switching power supply. Probably the biggest concern I have right now is that the no load detection. So when we turn it on without connected resistor, as you can see that we can't turn on the power, which is not ideal because you really don't want the voltage to be ramping up while you're connecting your load. You wanted the voltage to be stable. So we will have to, in our teardown, we have to take a look to see if we can at least bypass that. So now let me power it off, and we will open it up and see what we've got. And there are just 4 screws here holding up this top cover, and I think I can just move it away like this. And as you can see that the top cover, oops, there's a cable connected here. And but besides this ribbon cable here and a ground wire, and everything is pretty much cleanly separated here into the 2 sections. One is the main board in here, the other is handling the display, which we will take a look individually. And at the first glance, everything looks like extremely well built. This is really a high quality board. And if you look at the data code, these are components wise, these were from back in 1995, and some of them are from 94. And I can see that. So this unit probably was built, you know, at the 1995 mark, sometime right there. So to fully understand how a power supply like this operates, especially given it's a switching power supply, it can be quite difficult without knowing the exact schematics. And to map out the actual schematic is going to be quite challenging, as we have a lot of components here. But we can nevertheless just take a peek at some of the key components here and try to figure out the general principle here. So up to the corner here, and you can see this white component, that's a MOC 3063 zero crossing opto-isolator and triac driver. And further back here, we have a 2N6344A, which is a triac. So the combination of these two tells me that this unit uses some triac switching to control the output AC voltage, and therefore be able to control the rectified DC voltage. And of course, that AC voltage would be later on switched by this bank of MOSFETs here. So that's kind of the general principle here. And the MOSFETs back there are IRFP450, which are high voltage MOSFETs with a drain to source voltage of up to 500 volts. So we know that they are switching on the high voltage side, which means that the voltage after the triac and rectified is being switched by these banks of MOSFETs. And if we look further down here, we can see these TC1426 CPA. These are dual high-speed MOSFET drivers. And they are responsible for switching or driving these MOSFETs here. And it's interesting to see they are actually relatively far from these MOSFETs. So my guess is that the traces are underneath on the other side of the board. And if we look further down, we can see, what else we can see? We can see this is a CA3127W, which is a high frequency NPN transistor array, so there's nothing spectacular there. And here we have a LM566CN, which is a voltage controlled oscillator. So my guess is that this one somehow is responsible for generating the correct pulse width for the modulation to control the actual final high voltage being generated by this transformer right here. So there are some other chips around, and for instance, this one LT1014DN, I believe it's a quad precision op-amp. And so it's not surprising that we have an op-amp here, because we have to be able to compare voltage to the reference to be able to generate a stable output. And of course we have some other ICs here. For example, we have some gates and some flip-flops, and that's pretty much what we have on this main board. Of course we have some linear regulators towards this end, and that's actually pretty much it. So moving on to the display circuitry, and we have a separate PCB for handling the 7-segment display and its decoder. And on the bottom larger PCB, that one has our encoders for handling the front panel digital readings. And interestingly, we have a AD654 voltage to frequency converter. Actually, I have a couple of those. And so I'm not sure what those are doing here, but my guess is that they can be used as analog to digital converters. And also on the towards the side, we can see a Max 543 12-bit DAC. And as you can see, the entire digital circuitry is powered by a 68HC11 Motorola microprocessor, along with a, by the look of it, a EEPROM and SRAM. So the MS6264L, that's your SRAM chip. I almost forgot, one of the objectives we had before the teardown was that to figure out a way to disable the no-load detection. Because with the no-load detection, you pretty much cannot do anything without having the load connected. Otherwise, the power would turn off. And so by looking at the circuit board, I found this section, and here we have no load detect printed on it. So I think that this portion of the circuitry is for handling this no-load detection. And coincidentally, we also have this LM339, which is a quad comparator chip. So my guess is that one of the comparators will be handling this, one or more, I don't know how many, but will be handling this no-load detection. And again, without digging into the details, one way that no-load detection can work is you have a sense resistor and a reference resistor divider. And so when the current flows through, it generates a voltage drop, and when the voltage drop exceeds a certain reference point, then you will flip the output of the comparator. And that's how I think this unit uses to detect whether or not you have load connected. So now what I need to do is actually power it on and probe it while it's live. And the only thing is that it's pretty close to the high voltage section of the power supply. And you can see this very high voltage danger. And by the look of all these diodes connected in series, you know that we're dealing with a high voltage section here. But I think if I'm just probing the IC here, I should be fine. So what I'm going to do is I'm going to first power it on without any load connected, and to see if I can figure out what the pins are, the voltages are. So if you recall, for 339, the top 4 pins are the 4 outputs. So in theory, you can just probe these 4 pins, and first with the alarm going off, and then with the power on without the alarm, to see which pin, what state they are in, and hopefully we can figure this out. Okay, so now I turned the power on, and right now all the channels are off. So let's do a baseline measurement here. For that, I have to find a ground point, and there is a ground pin right here, so that's a test point. So now I'm going to measure each of the output, and we'll see. So I'm going to try to be very, very careful, because I don't want to touch anything that is high voltage. So for the first one, it's high, and it doesn't mean anything. We just want to see the second one is low, and the third one is low, fourth one is low. So one high, and everything else is low. Okay, so that's our situation here. So let's see one more time. Okay, so now let me enable the output. Of course it's gonna beep, but hopefully we can, because there's nothing connected. So now I have the output enabled. So now let's take a quick look. So this one, the first one is, let's see, originally was high, and it's still high. This one is low and still low. This one is low, it's still low. It's low. Okay, so nothing changed. Now, of course, it may be that that's the default position for these 4 voltages. So to really test it, we have to connect some load to it. And so I think if I connect the load to it, we should be able to see some differences. So I'm going to get the load connected here, and that's our 3 meg ohm resistor here. So now I'm going to connect the output again. So let's enable it. And let's wait till it stabilizes at 100 volts. Right now I'm setting the output to be 100 volts, so it's not a big deal. And so actually it's 79 volts, probably touched something, but anyway. So now let's go measure the 4 points again. So very carefully we measure the first one. It's 5, okay, not changing. And the second one, still 0. And this output, oh wait, this is a 5 volts now. So as you can see that this one changed the state. Originally it was a 0 and now it's 5. So the last one, this one remains 0. So I reckon that this pin, the very first one, actually it's not the first pin, but I think it's the 14th pin, that output pin, is actually responsible for sending the load detect signal. So now to just double check this, right now it's high, and I'm going to disconnect the load. So now this should be low, and bingo. So I think we have found out which pin is controlling the load or no load. So now let me turn it off. And oh, that's really annoying here. Let me just turn this off. So I think what I'm going to do next is to temporarily put a jumper wire between this pin and a pull-up resistor to our positive 5 volts, so that we will this pin would remain high. In theory, if our assumption is correct, this pin would be controlling the no load alarm, then we would essentially disable the alarm. So let me do that and we'll be back. And I just want to show you the temporary setup I have here. So as you can see, we have the pin 9 tied to the regulator, 5 volts regulator's output, so that pin 9 would be pulled high. And the reason we're doing that is because if you look at the pin out for LM339, we wanted the output 3 to be high, and by directly pulling that up to 5 volts is not ideal, because the input, if it is low, you're going to be competing with that output and going to cause some damage to the internals of the IC here. So an alternative way to do that, it would be to pull the input 3, which is pin 9, higher than the negative input 3, pin 8. So in this case, the comparator would automatically flip to output a high at its output. So that's exactly what we did. So here you can see that we connected this the positive input 3 to a 5 volt source. So let's give it a try and see if it works. If it works, we will make this a permanent modification. Okay, moment of truth. Let's power it up. And right now I don't have anything connected to the output, so let's enable the turn it on. And the good sign is we are not hearing any beeping, which is very good. So now you can see that it actually worked. So of course we can later on put it back to make sure that it indeed works as desired. And so that is actually a simple modification, just to make sure that this is working as desired. So what I'm going to do is I'm going to power it off and unhook this pin, and you will see that if we do the same thing, hopefully we will hear it complaining about no load connected. Yep, so as you can see, that indeed, that modification did the trick. So let me power it off. And I will make that a permanent fix, but I think that pretty much covered what I wanted to show you in this video. And of course I will solder a wire, I think, from this pin to an probably adjacent logic ICs so that I can get the 5 volts on it. But that's pretty much all the modification I need to do in order to disable the no-load detection circuitry. And with this modification, we can use this as a LED power supply. Now, of course, as we mentioned earlier, that this kind of electrophoresis power supplies do have some limitations. For example, the main limitation would be that it requires the load to be relatively constant, as it cannot adjust its output fast enough to compensate your load variations and the voltage changes caused by that. So that's one of the bigger limitations. And but there are some applications that you can definitely use this. For example, if the load is purely resistive or close to that. Another limitation is that as a switching power supply, and especially for this kind of supplies where the ripple current is not too critical, and you see that our ripple is relatively high for a power supply like this. So it may not be suitable for a lot of the applications, but that's just something to keep in mind. Nevertheless, this is a relatively cheap power supply, and you can get this quite readily on eBay. And I think I only paid about $60 some for this shipped, so it definitely adds some value to the lab. And I hope you enjoyed the video and learned something new. If you liked the video, please give it a big thumbs up and remember to share, subscribe, and I will catch up with you next time.